picture that you see whenever anybody builds a model. That is, you gather data, you build a model, and then you predict the future, right? That's what models building's all about, is predictive analytics and world domination. Next step. Just like all the other steps, no bigger, no smaller. Now, that may not be your cup of tea. You may want to instead fight fraud. Some people do that. Some people dominate the world. You may not want to fight fraud. You might want to do like today, we're going to save the planet. Ooh, we're so cool. So that's the one we're going to pick for today, not world domination. The sample problem then is we want to, in a small way, model energy use and help people understand what they're doing. It helps you guide what you're doing to fix things. It helps you find leaks, things that you didn't know were broken, and stuff like that. It increases awareness that people have of their energy uses, and it's found to save cost savings of 20% or more, just because people didn't know that they could do really cheap and easy stuff. And so let's save the planet that way. The way we're going to do this is a standard modeling methodology called the 5P model, ASHRAE. So it's got to be official. You see, they've got all these letters, so it's official. Stands for American Society of Heating, Refrigeration, and Air Conditioning Engineers. And they have a standard for building models of energy uses like this, where you plot temperature on the horizontal axis, and you plot energy usage, daily energy usage, or hourly, whatever you want to pick, on the vertical axis. And the idea is that in the mid-range, everybody has kind of constant use, their refrigerator, their 15 computers, that sort of thing. And when it gets hotter, they spend energy to cool. And when it gets colder, they spend energy to heat. And they assume that the increase in energy is linear with what's called the degree days, the difference from nominal as to the exterior temperature. Now, if we have a good model, this is what it looks like. You know, it kind of fits right through all the data. The altitude of that baseline looks like it's about right, and the slopes on the wings look about right. Here's a bad model. It looks fine, except for on the right, it just kind of goes haywire. Here's a really bad model. Now, I'm going to show you more bad models pretty soon than you can believe. But these are the ideas. We want to find good models like this, rather than bad models like that, or even kind of bad models like this one. That's the goal. Sounds pretty easy, but it's not. The reason it's not, and there's a couple of difficulties here. Some are political, or human, and some are mathematical. The human side of the problem is that we can't change what method we're using. We have to take as given that we're going to use this piecewise linear thing with a baseline and two wings. And the mathematical problem is that this is not a very nice kind of problem. Very small changes in those cutoffs will include or exclude points, and that will cause big changes in the wings or the level in the middle. And that therefore causes us to have a fitness surface, an approximation. As we move one of those cutoffs, we'll see the optimal error go up and down, not just down smoothly to an optimum in the middle. And that makes it hard to optimize. You can't use gradient type techniques on a thing like that because you don't have a nice gradient. You have a gradient, but it's up and down all over the place. And all of the parameters interact. It isn't like we can fix one, make it good, fix the next one, make it good, fix the next one, make it good. So these get rid of a lot of the easy ways to optimize these things. So often the next step is to use a more randomized search. It's not going to get caught by these small ups and downs because it's going to try a bunch of alternatives all around here. It's not going to try to use the local gradient. Instead, it'll kind of use general gradients, and it'll find lots of little pockets of goodness to find solutions in. So the basic algorithm is you fill a population with a bunch of solutions, You keep the best X% of them, and then you mutate the remaining to be kind of like what they are, but not quite. And you repeat until you're done. Works great, except for the fact that it takes geological time to converge. Now, that's one thing that a lot of the people, the fanboys for evolutionary and genetic algorithms kind of leave out, is that these can be extraordinarily slow algorithms. And the context here is we need to solve millions of these problems, not just one or two. And so if one takes long, a million is going to take a whole lot longer. So this doesn't work out so well. But with a very small change, just a tiny little bit of change there, this one line. If what we do is we use the previous step that we took as the indicator which tells us how big the mutation should be in the next step, then what happens is that the mutation rate mutates and evolves along with the solutions that we get. So it's kind of like a machine that has a hand sticking out the side that's reaching around and turning its own knobs. It's adjusting its own mutation rate, adjusting the rate that it finds new solutions according to what's working. This happens to converge very, very nicely. And the idea is that it learns using the fact that it's mutating the mutation rate to find the correct rates. Here's a picture that gives a bit of an intuition with that. So if we start up here, we're trying to find the bottom of the bowl. That's a very simple problem. If we start up here, we might take small jumps or big jumps. But right away, the big jumps, or all the best solutions, are going to be ones that just took big jumps. And so these little tiny jumps are going to die out. They're going to stay up here taking their little tiny jumps, and they're not going to get very far down there. And so we're going to wind up with a whole bunch of solutions down in the valley that are taking these big jumps and jumping down in there. Now, once we get down here, if we continue to take big jumps, we're going to jump right back up the other side or back where we came from. And so at that point, small jumps become preferred. And so the system will automatically learn at different strategies at different times. It will learn to take jumps that are roughly proportional to the distance to the final solution. And bad strategies will die out along with bad solutions that result. So that's kind of cool. But, there's always a but, this has knobs. Like, how big is the population? How many survive? What kind of mutation do we use? So we need to know where we turn these new knobs to solve these problems. And we've got this 5-dimensional solutions that are mass of mutating things in there, and we've got all these radioactive spiders. We have to figure out how we can understand what's good, what's bad, what's going to work better. We need to look inside the mechanism in order to understand that. So, I'm going to flip to some demos here, and what I'm going to show is how the constant mutation rate fails and how metamutation succeeds even on some difficult problems. And I'm going to show how the strategy shifts pretty much the way you'd like it to. So let's find cursor, yay, making progress. And let's make this a reasonable size. Now these videos were recorded a long time ago, interestingly. I developed this algorithm years and years ago. And at the time, I built these visualizations using TCL and TK. And it was very helpful in debugging this. So let's watch this for a little bit. Those are a non-metamutating system. They have a constant mutation rate so that they're making jumps that are about that big. Let's back up here. And so they never come to any kind of solution. They come in a little bit, and they never get any better than that. So this is the conventional sort of mutation where you just pick a mutation rate and they try to find answers. And they never really converge. That's the problem with the conventional algorithm. Here is the alternative that comes after this, and that's an algorithm where we use the step to adjust the mutation. They start in a very tight batch over there on the right. There it is. And then they learn quickly that they should be taking big steps to make things better. And so you see them start jumping with great jumps there. They took big jumps. Now they've determined that smaller steps are better, and they're getting tighter and tighter and tighter because they take smaller and smaller steps. Here it is going down a very narrow valley, and you can see them changing strategies. They first jump one way, then they jump the other. And the first ones were actually 5-dimensional valleys, so they weren't even 2-dimensional. Here it is trying to solve a very fractal-like spiral. So what we have here is a very flexible sort of algorithm, and here's some hints based on these old visualizations that I dug up the other day, that looking at how the thing works, how it actually follows these valleys around. You can't see the valleys because you can't see the actual thing that's trying to be optimized, but you can see the behaviors of the algorithm. And visualization is really helpful here. And unfortunately, these were built on toy-scale problems. And they worked fine for that. The visualization is fine at that level, and it helped debug the basic algorithm, but it doesn't actually help us with debugging the problem that we have here, which is millions of problems and actually more data. So the trick then is we'd like to use visualization to solve the big problem. The big problem, we're going to be running on a big parallel machine. We want to figure out what's working and what's not. Let's put on a show. Now, the current problem is 5-dimensional. The previous problems were mostly not. Problem parameters, the actual numbers don't make sense. You can't really plot it in an XY sort of representation. And we need to show it in terms of the actual problem itself. We also need to see dynamics in order to understand how this is working. The mainline system that we're going to be analyzing, or trying to assist here, has two flows. One is the development flow up here, which is where we developed this solver that we think works. And then we have the production flow over here. This is run on ordinary computers. This is run on a MapR cluster so that we can run at scale. Now, the data repository is on the cluster, but you can use both attacks against it because the data is accessible via conventional file I/O. Now, when we look at this, there's no real place to stick a video camera. There's no real place to stick anything, any tools that normally do visualization. We've got D3 over here that produces static visualizations of the result, but nothing of the process. So we need to figure out how we can make my standard tool, make some video out of that system. And there's a simple answer. And these guys know it really well. It's kind of like claymation. We make a picture, take a picture, let it move a little bit, take a picture, move a little bit, take a picture, and then glue it together. Now, if you're not careful, it's just as much work as it is to make Wallace and Gromit movies, which is excruciatingly amounts of work. Ardmore Studios produces, on average, about 3 seconds of video a day, which is just mind-boggling. It's no wonder they put so many jokes into the movies because it takes years to make anything, and the average number of jokes that anybody comes up with in that time get compressed 3 seconds per day. And so you wind up with a lot of jokes that you need to put in there. So what we're going to do is no clay. We're going to do a slightly simpler thing. We're going to take that solver from the scalable data chain that's normally producing JSON formatted models, and we'll just take logs out the side of it. And it'll record all of the candidates that it's evaluating along the way against all of the data it has. We'll throw that into parallel R and then into FFmpeg, which is a thing that makes videos out of frames. It does other things too, but that's what we want it to do today. Now, RevoScaler is a commercial product that scales R, makes it into a parallel sort of thing. It solves most of the parallelism, of course. We want to run arbitrary R. We have different kinds of codes that will produce these images and things like that. But we have problems. PNG, that's the thing that produces a frame of output, doesn't talk to HDFS. System, which is how we're going to run FFmpeg, assumes that it has access to an ordinary file system that's universal. And FFmpeg itself assumes that it's doing conventional file access. The easy answer, and I need to put my red hat back on, is that the MapR Hadoop distribution provides both kinds of access with the same file paths. And that makes this part of the problem fairly trivial. And here's some results. Here's some sample videos that are the output of the optimization process. Oh, there we go. And what we want to look at are, to start with, the 470 example, which was one of the last ones that came out. You can see that a whole lot of videos were produced here. Just a whole lot. There's the 470 video. Now here is the version of that that's being analyzed with 5 dimensions in the problem, to all degrees of freedom, and with a population of, let's start with 100 samples. You can see it mutating there. Now, thank you. Let's go ahead and just open that up. What's going to happen here is you can see lots of solutions here. Each one of them is just like the solution we showed before, has a flat spot and 2 wings. But we've got solutions that are plausible and some that are just highly implausible. It's an evolutionary algorithm, of course. And you can see after just a few generations, the very, very implausible versions have fallen away. When what we're left with is collections of fairly plausible things. As we keep going, though, it gets more and more tight. Now, this is the distribution of error down at the bottom, and that eventually becomes close to the minimum error. See, it's about 7.45. That's what it's got. Now, what's happened here is because the roughness of this solution is we've got a solution which is not optimal. The system has missed a bet. And if we are to look at here's another version of it, except with 500 candidates at any given time. Same 5-dimensional optimization. And watch it. So it's evolving. There's more candidates in there. And you can see that it's maintaining more variety as it goes. So already we've learned about something. And notice here, this isn't a flat line anymore. This has a kink in it somewhere in here. And if we look at the optimum values, they're about the same as we got with the other solution. But notice we're only half done, or less. Watch what it does here in a sec. At some point, a little bit of variation occurs, and something slips over the edge on one of these solutions, and the amount of variety spikes. Trust me, it does. There we go. Did you see it? Suddenly it says, wait a minute, somebody got a slightly better result, jumped over the edge of the precipice, and so it now started looking for a lot of variation in the system so that it could start exploring. It had a hint that there was a better solution just over the horizon, and so it did that, and it now found a considerably better solution at 7.42 instead of 7.45. It isn't big visible, but there's a kink here now, whereas there wasn't before. And this now has negative slope going out this way. And you'll see it do that one more time right at the end, where it suddenly says, wait a minute, maybe that isn't the best it could do. And so this algorithm was very, very adaptive. It found an optimal solution. Now, there's another way to solve this. We can take the centerpiece and just adapt that and the two cut points and leave the slopes for just a normal least square solution. We can solve that part of the problem. If we just get the center, then we can just solve the edges. We can't solve the problem in the full scale, but we can reduce it to just adapting 3 parameters instead of 5. Here's what that looks like. This is now adapting only 3 parameters, and notice there are no totally crazy solutions. Notice also it converges much faster. And so what we learned in the first one was that 100 was not a sufficient number of samples in the population, and so we had to go to 500. What we learned from the 500 is that there's a lot of wacky solutions that go in there, that we spend a lot of time exploring those, and so we could reduce the system to the 3-dimensional system. We now get much faster convergence with a much smaller population again, and it goes to the same solution. So these are intuitions that we get from looking at the system as it's running. The 470 system is that one, and then the 771 shows another problem. And this is a bit more of a real-world sort of problem, the sort of thing that we run into all the time when we try to build real systems. So this is pretty. You see what I meant by this massive seething spiders. So we've got all these 500 solutions. They're trying to find a good answer. And look what they're converging to. You know, the mass of the data is here, and they're converging to a solution that's down here. And the reason doing that is because this house is unoccupied a lot of the time. And so it's trying to split 2 models, the model of a house that has no power and a house that has people in it that are there only in cold weather or neutral weather, never in hot weather. And so what it's doing is it's splitting the difference there. And this is an interesting case because research houses, if you think about it, never go unrented, because the renters and the government always pay the bills. And that means that the experimenters, the researchers, never see a house that looks like this. And just like always, whenever we build a system, what happens is reality is inventive and it breaks us. Things don't work the way we expect. So there's lessons that we learned from looking at a system dynamically. And the interesting thing here is that we can do this very easily. We don't have to use a big machinery there. We can learn very important lessons from these systems just by pulling back the covers a little bit and trying to see how they work inside. Seeing in a real visceral sense, seeing how they move, how they live, how they evolve, and how they get to where they are. We can make substantial improvements in our optimization systems by doing that. And then we can also then take this one further level, and we can actually use these models, because a model can be considered to have a distance to a model or to a data set. And at that point, we can start clustering our data sets, not in terms of traditional clusters, but in terms of the models that describe them. This data set here has 2 kinds of things happening, this kind of thing and this kind of thing, the unoccupied kind of thing and the people who are there in cold weather kind of thing. And so we can cluster that, find those 2 kinds of days, and we can cluster our data now in terms that people understand. These are some of the things we can do with nonlinear optimization and a bit of visualization. And remember, there's a prize in every one of your boxes. It's a USB stick with some software on it. Do we have any questions? We have 15 minutes to go, and we can have any number of questions you like that'll fit in 15 minutes. It's a knapsack problem. Does anybody do problems that smell like this, with optimizations, unfortunate model structures imposed on them, difficult optimization processes? Yeah, questions up here. Hold on, we'll get a microphone to you really quickly. Yeah.
watching this visually, it seems very seductive to overfitting.
It is a problem in any system. You have a trade-off. You can explore forever and guarantee that you never overfit, and that you always will find the global optimum. And it will take nearly infinite time to at least as far as I'm concerned, to find that answer. Or you can accelerate that convergence, and you now stand some risk of missing the global optimum in favor of a local optimum. And you have to trade the resources for complete exploration versus get an answer now. In the first case there we had, the 5-dimensional case, we made the trade-off wrong initially. We had a small population, and 5, 10, 15% of the time, it found a local optimum rather than the global optimum. When we increased the population and increased the cost by 5 times, by going to the 500 population, we never found an example of it not finding the best known solution. But it cost more. Then by decreasing the complexity of the problem, there's many, many more corners to look in 5-dimensional space than there are in 3-dimensional space. You know, there's only 8 corners in this room. But in 5-dimensional space, there's 32 corners. And so exploring things in a lower dimensional space is much easier. And so we were able to do with a smaller population again. That wasn't understood right away that that would make such a big difference. So you have that trade-off, absolutely. This particular thing is not superbly prone to overfitting. It doesn't do that so much. If we go back to the 470 example, if we have enough examples, it's exploring well enough that it overlaps and always finds a good solution. It never overlooks that because the good solutions are close enough to the at best solutions that it'll find them. It'll overshoot a little bit. Some of the examples will get over there, and then it jumps in, and everybody converges to the best solution. But you're right, that's a problem. That's always a problem in nonlinear optimization that's not a convex problem. We have another question here.
What do you use for a mechanism of convergence criterion, or do you do some sort of post-point-in-time sampling of your parameters?
Well, for the video here, my criterion was I got bored. So, you know, that's always a useful one. But a better one is usually that we have stability, that the mutation rates have gone down, and the diversity in solution quality has become near zero. Because once there is no mutation, and once we had higher mutation and we're now down to smaller mutation, the system really cannot get back out of that. Now, as we saw in this one, it can be misleading because it can be pretty stable looking, and then somebody just gets a hint, and it suddenly a big step becomes very valuable, and everybody's doing it. So it's a difficult thing to do, and it would have been pretty easy to call this one too soon. But it did not actually converge. It still had a couple of degrees of freedom in that population, and it was still changing. So it wasn't ready to call. And then luckily, it did jump over that edge. This is the only one I've found that's that close. These are highly selected examples, so we don't have to walk through hundreds of these by hand. But that's the sort of thing you do, is you look for anomalies. You look for different solution methods to see who produces the best answer, and you find where you aren't doing the best. And watch those things like a hawk to figure out why. And that's when you find these things. That's when you get to adjust a knob so that never happens again.
So do you have a sense of how you would weight your mutation rate of decline to your parameter change rate of decline? I mean, like the traditional, let's do a parameter estimation exercise, Bayesian-wise, is kind of wait for post-hoc or post-burn-in samples and then take a whole bunch of samples of those
Yeah,
and
yeah.
aggregate those and use
So
them.
that's one of the fun things about this thing is it learns that as it goes. It adjusts all of the mutation rates according to, it evolves them just as it's evolving the solution.
Yeah, so you've added a second parameter to your convergence measurement.
Well,
the
actually
mutation.
not. All I do is add one history element. And then there's one unidirectional mutation as well. But otherwise, in high dimensional space, what you wind up doing is you have n squared as many mutation parameters as you have parameters, n. And then to mutate those, you have n to the fourth parameters, and then it just gets out of hand. Here, what we've done is we've recorded the last step and the current step, and one omnidirectional mutation. And so the directional stuff is proportional to the last step, and it goes both ways, but prefers to go the same direction. And the omni is self-similarly mutated. So it encodes its own mutation rate, and then it couples with the directional. So that if it goes really fast one way, it's going to get some omni out of that as well. And so it'll explore around that. So it's self-encoding the mutation rate in its own history. And that's a key point to avoid that explosion. There's paper online if you'd like it. Send me email. Also, all the code is available in the Mahout package. So all of this is open source code. Is there another?
Any more
Somebody
questions?
is reaching.
Raise your hand.
So you sound like you have optimization problems. Are there other people here who have optimization or visualization problems? Where should we go on this sort of thing? Anybody got an opinion about that? Everybody came here and ate my popcorn, and they're not going to say anything back. Now, that's just not fair. Somebody's saying something back there. I can't hear it. Yeah. Odds and risk information estimation. And then with odds and risks and that sort of models, those are complicated models, and they have lots of nonlinearities. And so this sort of algorithm, or some sort of MC, Markov chain, or Monte Carlo of some kind, is very, very commonly used for these optimizations. So these may be the only financiers in the audience, but I think there's other people who have optimization problems as well. But if not, I'm going to call it 5 minutes early. I'm happy to answer questions offline afterwards or at the reception in the exhibits area. So come up and let's talk. Thank you very much.